I really love presenting at the Friday seminars. It's one of the joys of working here at the SMI. And normally I do dress up quite a bit more than I have today, but I thought it's my last day of being a researcher. So when else am I going to wear my ape shirt and my handmade shoes? So I don't know if the new workplace is going to allow this kind of dress, but I'll find out sooner or later. So, and thank you for my wife and my children turning up. You might hear a few daddas and stuff like that during the thing. It's very special to have them here to be able to listen to me and see what I do for work. So I've presented, this is my 6th Friday seminar that I've presented over the years. I just, in preparation for this, went back through the different Friday seminars that I did. I did 2 when I was a PhD student on dielectrophoresis, which my wife always said makes me sound like I'm dealing with dinosaurs, but it was an electrical separation technique that's actually creating a little bit of interest in recent weeks. Some people from the European Space Agency have been contacting me to see whether they can use this in space, which is really quite exciting. And then I've done 3 more presentations since I've been a staff member here, generally on energy efficiency and energy efficiency in comminution. So today, when Susanna asked me, it wasn't actually meant to be the presentation for my final day, but I'm going to use it as a bit of a valedictory. I'd originally planned to do a presentation that I'd done in Brazil. I did a keynote for Mezzo in Brazil, and that was my original plan for the presentation, but when I started putting it together, I wanted to put a bit more technical detailing for the crowd. So I got about 1/3 of the way through the actual presentation that I did in Brazil, and I went, that's probably enough. So I'm presenting 1/3 of what I presented in Brazil, but it's much more technical detail, so hopefully that interests everyone in the audience. But the main scope behind the presentation in Brazil was something that I've been looking at over recent times, and that's strategic prioritization of different technologies and techniques for mineral processing. And one of the things that I've come across is this impact ease matrix. It's something that's used widely, less so I think in mineral processing at the moment, but it has been used widely by different agencies to rank different technologies. Sorry, I'm in your way here. I'll stand a bit over in the corner. The idea here is to rank different technologies on their ease of implementation on the bottom, and the impact of that technology on the vertical axis. What you find quite quickly when you do this kind of technology is that things normally sit in this kind of a band. There aren't many technologies that are really easy, that are really hard and have low impact, because you normally just say no to those before you even get to this stage. And there aren't many that are very easy to implement and have a high degree of impact on the top end. Those typically people think that they exist, but they don't actually exist. So I'd say this area you'd say no to, and there for my daughter is the sparkling unicorn that you never actually find but you're continually chasing after. Now in between this, what I started to realize was that there's no increased value in necessarily increased value in a project that's here or a project that's here. It's just different ways of thinking about technology. And actually what you want to do is split this up into a time frame. So I combined this with the 3 horizons approach. So you kind of have the technology that you want to implement now, down here, near, so in the near horizon, and the next horizon up there. And you'll use different people to do these different jobs. So the now might be the site metallurgist, the near might be some consultants, the next might be some research organizations. So once you start to prioritize these different technologies in this way, you can look at how you actually do the technological advancement. So just as a case study, and this is what I did in the keynote, was I presented 3 different technologies. So pre-concentration, for instance, really has a low level of ease. It's ore dependent. It can be quite hard to implement with the mine plan and those kinds of things, but it has the potential for a high impact. So that really sits in the next sphere. Cyclone optimization, it's something you learn in undergraduate. it doesn't have a large degree of change, maybe it's a 10-15% improvement, but it's relatively easy. So that might sit in the now sphere. And high pressure grinding rolls are some kind of new technology that has the potential to make a big difference, but needs some extra work, and it might sit in the near sphere. So in the keynote, I presented these 3 different areas and presented it with the energy curves methodology. In this presentation, I'm going to concentrate on the now sphere, and specifically some work that I've done over the years on size-specific energy, and some of the more recent advancements that have actually come in the last couple of weeks, which I'm starting to get really excited about. So it's new research that's going to be presented. But before we get into the new research, one of the things that I'm going to be using is the Comminution Energy Curves. And this has been something that I've developed while I've been at the JKMRC. And it's actually thanks probably largely to Tim Napier-Munn, who, when I presented a Friday seminar in 2012, came up to me afterwards and said, "We really need you at Noosa for the SEEK workshop up there. Have you been invited?" And I said, "No, I haven't been invited." And I went up there and I was able to write the blog for the workshop. But out of that, just being a fly on the wall and listening to people, I realized that there was a real need for a energy benchmarking methodology. And so I went to start developing that. And that's where the energy curves came from. So essentially what they are, I took the idea from the cost curves, because that's something that a lot of people understand, is easy to comprehend quite quickly. Essentially, you have a whole lot of mines. Each mine is represented by a bar. The height of the bar represents the energy intensity, and I use a number of different metrics for that, because you can't really talk about energy intensity in one single metric. The width of the bar, it represents the annual production in the database as a proportion of the full database. So essentially that, and the mines are ranked in increasing energy intensity. So that's how you read an energy curve. For those of you who haven't, I've been preaching about them for a number of years now, but for those of you who haven't seen them before, that's how you read them. And here is one of the energy curves. So this is the most basic energy curve that has specific energy, the kilowatt hours per ton that is used in the ore, and you can see all of the mines there. Now the database that this is based off is quite large. It contains about 33% of the world's gold and about 60% of the world's copper, as well as a number of other commodities. And actually, I was doing this presentation for VW, and I thought, how can I actually talk about the size of the database? So I went and I looked at how much energy VW Golf consumes, and equated that to how much data was in the database, or energy was in the database. So it's the equivalent of a VW Golf circumnavigating the globe 1,700,000 times. So it's a lot of energy that is consumed by the mills that are in the database. So that just shows how kind of big the database is and how energy intensive milling actually is. So what you can do with the energy curves is you can have a look at the full shape, but you can actually, if you have a mine that say has a 25 kilowatt hours per ton energy power draw, you can look at where that would actually sit on the curve, and that mine sits at about the 80th percentile of all the mines in the database. And then looking at different technologies, whether they're in the now sphere or the next sphere, you can visualize the movement down that curve and kind of provide an incentive for people to be using energy efficient technologies. Quite a visual technique, but yeah, so that's the basis of the energy curves. So I'm going to be using those a lot in the coming sections. But before I get into the actual crux of the presentation, one of the other things I wanted to just show was recently there's been some funding by the Queensland government and the federal government to advance this energy curves methodology through METS Ignited, and SEEK has helped sponsor that. And a number of really good outcomes have come from that. Firstly, we've incorporated energy cost, not just the specific energy consumed in terms of megawatts, but actually the dollars. And the way we did that was I did something that I found really interesting, which was work out the energy density around the world. So I found a database that had the production of energy from different power plants at different points in the globe. And from that, I was able to create a methodology that kind of had an energy density around the world. So this shows you the blue is low energy density, so there aren't that many power plants there, and the yellows in US and Europe are high energy density. So that's high watts per meter squared or megawatts per kilometer squared. And what I did was I related that to the variability in energy pricing, because the variability in energy pricing varies by about a factor of 10 within a country and between countries around the world. And so I needed to use something to take into account that variability, and this is the methodology. The second thing we looked at was the ancillary equipment. Because if you take into account just the energy that a mill is drawing, you don't get the full picture. And some mills, like an HPGR versus a SAG mill, require significantly different ancillary equipment. So lots more conveyors, and actually it was a comment from Marco when he was going to different plants with HPGRs. And they were just installing HPGRs. He realized that actually you had to take the kilowatts of the HPGR and double it, because the kilowatts of the HPGR effectively equaled the kilowatts of the extra conveyors that you needed to install to be able to run that HPGR. So it was from that comment that I then started this ancillary equipment project. And what we did found, we created a methodology that looked at the linear distance of conveyors, and an SABC circuit or a SAG milling circuit typically has about 600 meters, or a typical SAG mill circuit can have 600 meters of conveyors, and that equates to about 1.2 kilowatt hours per ton. But some HPGR circuits can have up to 3.5 kilometers of conveyors, equating to about 5.8 kilowatt hours per ton. So there's a significant advantage if you don't design your circuits to minimize the conveying, and that needs to be taken into account. The other one was embodied energy. So this is the energy embodied in steel grinding media. We put steel grinding media into our mills. They get consumed through abrasion, but that steel had to be mined, had to be smelted, had to be forged, had to be transported to site, and there's energy associated with each one of those steps. Some original work done by Morrison and Musa found that that could be up to 50% of additional power draw added to the mill power draw, essentially, if you take that into account. So they had one case study, so one mine with 3 different mills. I was able to find data on significantly more mills. So this was the data of just the mills. Then I had about a little bit more circuits that I didn't put on this graph. But so this is the dark purple here is the power draw of the actual mill. And when you then take into account media consumption and the energy associated with all of those stages, it can add somewhere between 15 and 43% to the energy consumption if you take that into account. So if you look wider and take that media consumption into account. And what else is interesting, it didn't seem to be dependent as much on the actual equipment type. I was expecting SAG mills and ball mills to be significantly different. They weren't, which was interesting for me. I don't know exactly what the driver is behind that. I didn't investigate that too much, but it seemed interesting. We also looked at circuit type, and next we'll have commodity type. And what we did in this, I'd like to do a little bit more on this, but this is where we got to. We were able to isolate different circuits, but instead of drawing a new energy curve for the different circuits, because that would involve fewer of those rectangles, and you might be able to back calculate which one's which and remove the de-identified nature of the data. Instead of that, we fitted log normal distributions to the underlying distributions of those circuits. And we could look at the distribution of each one of those circuit types with that graph. And then also we have the same thing with different commodities, where we have the megawatt hours per ton copper equivalent, and we're able to split out different commodities with log normal distribution. So that shows you kind of the mean and the distribution of the underlying data without compromising the anonymity of that data as well. And finally, something that I'm actually going to go into a bit more detail in the coming slides was the calibration of the fine grinding. And this was really interesting, looking at size-specific energy, looking at different marker sizes. And I'll go into detail with this exact case study in the future slides, so I won't ruin it by showing you too much there. But we were able to calibrate for fine grinding in the process. So, getting into the meat of the, I don't have much time left, I should have not had as much of an introduction. But we'll get into the meat now. So, size-specific energy is something that I've been developing for a while, and it comes from this basic understanding. The Bond worked with the typical circuit of the time in 1950. Closed circuit crushing, open circuit rod milling, closed circuit ball milling. And he came up with the fact that P80 could be used to measure the size reduction of each one of those equipment. But he had the caveat that this only works if the size distributions are parallel in log-log space. And I didn't have any data from a circuit that looked like this because I wasn't around in 1950. But I do have a similar circuit with tertiary crushing and 2 stages of ball milling. And you can see that those size distributions are essentially parallel in log-log space. So these kind of circuits, you can use P80 to describe the size reduction. But as most people will know, circuits aren't like this anymore. Most circuits aren't like this anymore. Circuits nowadays can be like a sag mill, where the size distributions don't necessarily follow that parallel in log-log space formula that Bond originally said. So P80 isn't a really good marker to show you the size reduction that happens in each one of these steps. If we use P80, the sag mill trommel undersize, the P80's up here somewhere. And so it says we're not doing as much reduction as we actually are. There's a whole lot of fines that are generated by these sag mills that isn't accounted for if you just take into account the P80 of the size distribution. And the same is true of HPGR circuits, but to a lesser extent. This is an HPGR circuit that we surveyed, Tropicana, and you can see that the size distributions of the HPGR screen undersize is slightly flatter. And when you do the regression, you actually know how much that is. It's hard to tell on the actual screen here, but it is slightly flatter. And there are other circuits that these size distributions don't stay stable with time. They depend on a number of different factors. And these are some size distributions from Cadia. What's interesting here is that at different points in time, the HPGR product, for instance, can be flatter or sharper with the same P80, but be generating more or less fines. Now that's a relation. That's related to the pressure in the HPGR. Higher pressure, you get a flatter size distribution, you create more fines. But you don't necessarily change the P80 too much. And sag mills as well can be flatter or sharper. This is largely due to the rock to ball ratio. So when you have finer feed, you need to increase the balls, and you get a sharper size distribution out. And the ball mill cyclone over time can be sharper or flatter as well. And that's normally dependent on the actual cycloning efficiency. So none of these size distributions are actually parallel in log-log space. So it doesn't make sense to be using P80 to describe the amount of size reduction that is happening with these modern circuits and different type of equipment that's set up. So what Malcolm Powell really encouraged me to do was to look at size-specific energy, something that he coined in 2012, that, as we'll see, has been used for a long time before that. So if we look at what I was saying is if you use the operating work index, so this is a case study done by someone in the workroom at a mine site in Australia. Really fascinating having a ball mill and a SAG mill in the same circuit, doing multiple different surveys of that ball mill and SAG circuit over time, and looking at the operating work index, which is the kilowatt hours to reduce P80. So if you take into account P80, this is the outcome you get. The SAG mill, in this way of analysing the data, looks to be about 3 times more energy intensive than the ball mill. And this is something we've known for a while now. You can't use the P80 to analyse a SAG mill because it makes the SAG mill look really inefficient. And this has led to a lot of people saying that SAG mills are really inefficient. They are when you look at P80, but when you look at the fines production, as I'll show you, they're not necessarily. So this is the site-specific energy, the same data, the same 7 surveys, the same SAG mill and ball mill. But now instead of looking at P80, we're looking at the production of new fines, the production of minus 75 micron. And as you can see, the SAG mill and the ball mill come out very similar across this. In fact, in 3 of the surveys, the ball mill was more efficient than the SAG mill at producing new 75 micron. But in 3 of the surveys, the SAG mill was more efficient than the ball mill. So this said to me that, and one of the surveys, they're essentially the same. This said to me that if we compare this, looking at the fines production, this might give us a way to fairly compare SAG and ball mill performance. But I've got to say that this isn't the first time this has been done. And the further I look back, the more I see people that have done this. And I'm amazed at the names that come out of the picture. The first person to have done this that I've been able to find as yet was actually Davis in 1919. He looks at the kilowatt hours per tonne. Interestingly enough, 74 micron. Everyone seemed to have used 75, 74 micron as the marker size in all of these things. Hookey also used it in 1968. Mocken, we found out from Greg, used it in 1979. Shonit, which I was really impressed by, following in Shonit's footsteps, 1988. Levine, that was actually the first one that I was aware of right at the beginning of doing this project. Musa, Hilden, Powell from here in more recent times. But so this isn't a new thing, but I guess what has happened in recent times and with Malcolm is the formulation of a methodology and an actual metric. The site-specific energy term came out of that. So that's really been the change in recent times. So if we look at another case study, this was one of the first case studies that I worked on. This was Sunrise Dam. We did a survey there. They had 3 stages of crushing and 2 stages of ball milling. And you can see the outcome for the crushing and the ball milling on this graph. This is the specific energy and the 75 micron generation. Now, what this shows us is that actually the second ball milling stage is generating more 75 micron for the energy consumption that's actually occurring. So there's actually a potential, if we're able to bring this circuit 1 either back down here and use less energy for the same 75 micron or up to that line, there's a potential 10% opportunity to move the total circuit, and that's a 10% opportunity in throughput essentially. So this is a really simple way of displaying the data that gives a really easy implementation for site. And what we found, and we've done this a number of times now, is that the simulations actually back this up typically. When we do the simulations, they show us similar amounts of improvement that could be gained. And we can look at that on the site-specific energy curve as well. So this is just a different way of displaying that exact same data. So the different mills can be represented as data points there. And the potential is that the total circuit can move down that curve as you improve the efficiency of mill 1 and the crushers down that curve. What I really liked about this was that it gave me a way of displaying the opportunity as well. Because the site-specific energy has kilowatt hours per tonne minus 75 micron generation, you can convert that to the throughput at different grind sizes if the kilowatts stay the same, if the mill has the same power. And so you can see with the current efficiency, as you increase your P80, your throughput can increase. But if you improve the efficiency, there's the potential to increase the throughput at the current P80. And that's where the 10% opportunity actually comes into play there. So you don't have to coarsen the product to be able to get that throughput benefit. So what we realized very quickly was that we could only benchmark against the other equipment in the circuit. We could only benchmark one mill against another mill using that methodology. So we've tried to develop a method to be able to get a laboratory line in there. And this is some work from a master's student that we had, Yogesh, who looked at can we draw with the same ore from site, can we draw a laboratory line on there? So this is the site data, different site, what the laboratory equipment can do down in the pilot plant, and then so to benchmark the opportunity of that, or whether we can do single particle breakage. You can see the data points down here, but the opportunity is to move that way. This is where the student got to. It's very difficult to produce minus 75 micron in single particle breakage. So there's a whole lot of missing data here. He was doing single particle drop weight tests, essentially. And that's where the idea for a rolls crusher came in. And if anyone wants to see the rolls crusher, it's just down in that room. I'm sure we can have a tour or something like that. But this is the rolls crusher that we bought, and we've been doing some testing on. Essentially, what the aim of this is that you have single particle breakage as it goes through the rolls, and you can accurately measure the torque that's consumed by those rolls, and it's essentially the input energy to the particles. And because of the way the rolls are machined and the accuracy of the machine, we can actually go down to a feed size of about 150 microns, which starts to generate a lot of 75 microns, so we can start to draw that line quite accurately and get the rest of that missing data. But there is another way of doing this that I've been exploring in the recent weeks, and that relates back to Bond and Morel. So we could use that machine to benchmark the single particle breakage, or we could use methodologies that are already widely used in the industry, so the Bond and the Morel methodologies. But first of all, we need to find out what the equality between Bond and site-specific energy actually is. So what I did was I created a whole lot of size distributions that were parallel in log-log space. So I used the Gauden-Schumann relationship to be able to develop those size distributions. So this is essentially, Bond is accurate when the size distributions are in parallel and log-log space. And also Bond suggested that the exponent in this Gauden-Schumann relationship was typically 0.5. It's actually in his original papers, that when you do that analysis, it's typically 0.5. And when you put in 0.5 into that relationship, what's interesting is that, and you do the same for site-specific energy, so you use 75 micron to benchmark that as well. What's interesting is they actually come out mathematically exactly the same with a factor. So when the exponent of this is 0.5, site-specific energy equals 1.44 times operating work index. So they're mathematically equivalent in their process when the size distributions are parallel in log-log space. So I got very excited by this. I thought this was really interesting. That by looking at the fines, we can actually get the exact same outcome as the operating work index when the exponent of the size distribution equals 0.5. So I started looking at the Morel as well. And what's interesting is that when you use the exponent from Morel in the same Gauss-Schumann equation, that's the exponent that Morel looked at. So it changes the slope of the lines in each one of them. But you do site-specific energy on that, and they're equivalent as well. They're not mathematically equivalent, but they're essentially the same, if that makes sense. So not to 20 decimal places, but maybe to 1. So this is really, really fascinating. So there is equality between Morel and site-specific energy, bond and site-specific energy, when those exponents equal what Bond and Morel said they should. And that led me to think that maybe site-specific energy is a more general case, where Morel and Bond are more specific cases. And the other added benefit is that the site-specific energy allows you to deal with non-parallel size distributions in a realistic way. So that was a really interesting outcome. But that wasn't where I wanted to stop. What I wanted to use was the Morel and Bond laboratory testing to be able to benchmark the site work. And so I came up with a methodology that I'm going to be using in a paper that will be published in the SAG conference. So back to the same graph that we had before, the 75 micron generation and the specific energy. If we have the different equipment, this is another case study. 2 ball mills in this case study and a SAG mill. The total circuit sits up there. So if you drew a line, you'd be able to say that potentially the SAG mill is underperforming in comparison to the ball mills in this case study. But that's all you'd be able to tell. Whereas what we can do is look at the P80 of the total circuit. Bond still works across a whole circuit because the primary gyratory crusher product is still parallel typically to the cyclone overflow in log-log space. So you can do Bond over an entire circuit effectively. It's just not very good at individual pieces of equipment. So when you do it over the whole circuit, you can get the kilowatt hours per ton that Bond says should be happening, and at the same generation of 75 micron, and draw a line through that. And what this allows you to do is say that the total circuit in this case is about 80% efficient in comparison to Bond, but we can actually benchmark each one of the equipment as well. You can see the ball mills are actually more efficient than Bond says they should be, and the SAG mill is significantly less. So it gives you an indication, at least, based off a laboratory test that is trusted. So my final case study is this Salcedo case study. So in this we did 8 surveys, myself and a student of mine, Juanjo. And the main aim of this these surveys was not to get site-specific energy. It was, we were looking at the difference between running the circuit with screens and with cyclones. Really interesting case study, but I thought some nice data came out of this as well. And what you can see in this case as well, when you look at the site-specific energy, in 3 of the cases the ball mill was more efficient, and in 5 of the cases the SAG mill was more efficient. So once again you had that kind of equality between the site-specific energy of each one of the equipment. But as you'll see, we didn't use 75 micron in this case, we had to use 53. Because the P80 of the entire circuit was about 50 micron. So using 75 micron didn't make any sense. You couldn't use 75 micron as an effective marker size. So this got me thinking, how can we move from 53 to 75? Or how can we move from any marker to any marker size? Because different mine sites. There's nothing special about 75 micron, there's nothing magical about it. Different pieces of equipment, different mines will have to use different marker sizes. So that's when I started looking at the relationship between the site-specific energy at a specific marker size and the size. Now this is the results from the SAG mill. And what you can see here is a number of parallel size distributions, parallel lines here in log-log space. There are 2 that don't quite conform to that. But interestingly enough, we saw the exact same result with the ball mills for those 2. So I think it's something to do with the actual mineralogy of those samples. But the rest had nice linear relationships in log-log space, which makes me think that there's a relationship between the size and the size-specific energy. And so that's the sag mills. Now if we go to the ball mills, you can see a totally different relationship. But what this is showing us is that there's actually a spot here where there's an incorrect marker size. We've moved to a marker size that's too coarse for these ball mills. Remember, they're grinding to a P80 of about 53 microns. So we can use the gradient on this side of the graph and extrapolate that out. And you can see these two surveys, they were the two surveys that were unusual in the sag mill. And you can see they've got different different gradients there as well. So that allows us to get an effective size-specific energy at 75 micron for each one of these mills by extrapolating down. The other benefit of this is that we can do much finer grinding. So an isomill might be up here somewhere, and we can extrapolate down. Crusher might do something else at the fine end, so we can extrapolate up. So with this methodology, we can effectively use an equivalent measure for efficiency of crushers through to isomills, using the same essential methodology. And this is just two of those case studies where you've got the sag mill and the ball mill together. This one on the left was actually low density in the ball mill. So you can see that the ball mill was less efficient than the sag mill in that case. And in this one, it was high density in the ball mill, and the ball mill was more efficient. So you can see how they kind of relate to each other as well. And we could now, because we're extrapolating out, we could put those on the size-specific energy curve at 75 micron and show the difference between the two curves. Now I thought I'd do a sideways jump into fractals here, just to impress Dion that I actually listen to him sometimes. Dion presented something at a Friday seminar a number of years ago now. I don't know how many remember it. It's ingrained in my memory because it sparked a lot of ideas. And that was that we can describe size distributions as fractals. And I've always loved fractals, but I've always thought they were just pretty pictures like these pictures up here. I didn't actually think of them as something useful that we could use in mineral processing. But essentially, for those of you who don't know what fractals are, they're patterns that look similar at different magnifications. That's how I like to think of it. So you can look at these patterns at a large magnification, and they'll look very similar if you go to a smaller and a smaller and a smaller magnification. And we see that effect in size distributions. And what Dion made me aware of was a guy called Turcotte, who looked at plotting these size distributions in log-log space. But what he had here was the radius of the particle, or is it diameter? It's r, so I assume it's radius. Should be equivalent. And the number of particles. So here it's obviously the opposite way of a size distribution that we like to think of. But what he found was that these were linear in log-log space, and the gradient of these size distributions was equivalent to the fractal dimension of that ore. So it's a box counting algorithm. You can talk to Dion more about this afterwards. He knows, he's much better at explaining it than me. But that relationship, that slope of that line, is something characteristic of the ore and the breakage device. And it's related to something fundamental, the fractal dimension. Now what we can do, we don't look at the number of particles, but we look at the percentage passing in terms of mass. And when we graph that on that same thing, we typically do see a linear size distribution in log-log space. But in this case, the fractal dimension is 3 minus the slope of that graph. And that gives us we can use our percent passing graphs to actually get the fractal dimension of the particle size distribution. So I thought that was a really good, really interesting thing. And what's interesting is that when you go to this size-specific energy marker size, that gradient is actually related to the gradient of the size distribution. So what you get is actually, if you look at the gradient of the size-specific energy, it's actually equal to the fractal dimension plus the slope. Essentially, the negative of this is equivalent to the slope of the size distribution. So now we've got something that's potentially valid from fundamental principles, which I really like. And so I collected a whole load of data sets rather than just having one data set for you guys to look at. I've got 250. So you can see the slope of all these lines is pretty consistent. They're similar slopes, but they all have a typically linear relationship. What's interesting is the slope of that line. So if you look at a frequency distribution, and we convert that slope into the fractal dimension of the ore, you can see that they typically range between 2.5 and 2.75. Now, I've raised this with Dion, and he said that it's realistic, potentially, and they actually relate to different ways of fracturing. So when you get up into higher fractal dimensions, it's more of a pulverization that's occurring, and lower, it's more of a bulk splitting, but that's more around 2, right down this area. But what's interesting is that that's where Bond kind of sat.